or most of you, they probably have cell phones, and you wonder why does it take so long to download something? And today we'll tell you the answer of why it takes time to upload and download information, and why it doesn't all come infinitely quick, okay? Questions? All right, so first thing I just want to do is I'm not going to try and draw the picture of a wave traveling in space, but we showed last time, well, let me start with the beginning. Is Leo here? I don't see Leo. Okay, Leo was here last time. No, it was Yazoo. It was Yazoo. We said we had a plus and a minus charge. A plus and a minus charge going up and down. And we had a plus and minus charge going up and down. There was an E field out here, electric field, which was going up and down as these charges reverse position. And we said if these charges are going up and down like a sine wave, if I looked at the electric field versus position, let's call this the y direction, the electric field versus the position would go up and down. So meaning the electric field right near these charges would just be what you get between the two charges, but then it took time to go in that direction, and so that's why it's different. We'll go away. So the electric field was going up and down, and you can show that if the electric field is going up and down here, that was the electric field. There's a magnetic field. There's a magnetic field going back and forth in that direction. That the electric field going up and down creates a magnetic field going up and down in that direction. And this whole electric and magnetic field, which are going up and down as a function of time, propagate in that direction. And that's light, that's radio, that's X-rays, that's sunlight, that's TV, that's radio, all the above. That's what it is. And the velocity of this thing in vacuum is equal to c, and if you're in a material, it's, maybe we should write c over n if you're in some material. And it's an electric and magnetic field at right angles to each other propagating. Questions about that concept? Okay. Let me give you an example. You were looking at me. There's light, it's light bulbs, hits me, goes to you. Those are different rays, and some of the rays that go from me to you might have their electric field this way. Some of the rays might have their electric field this way. Some might have the electric field this way. There could be all different directions of electric field. Because, again, if I'm going in that direction, I wrote the electric field going up and down, but the electric field could be going in this dimension, and which means the magnetic field would be going up and down. But the main thing is that the electric field and the magnetic field are right angles to the direction of the ray. So let me give you an example. Here's a piece of plastic which has been engineered. It's been engineered to absorb light when the electric field is, actually I don't know if it's pointing up or down, but let's assume this piece of plastic absorbs light going through it when the electric field points up. So you notice I'm not as bright, right? That's because the rays of electric field pointing up get absorbed. The rays that are electric field that way go through. So say, well, on average, half the light you go through, and you don't see me very much, and I can rotate it 90 degrees, and then I absorb the light in the other direction, but I still have light coming through in the first direction. These are called polarizers. There's a polarizer. Meaning the light comes into the polarizer, has electric fields in various directions. that goes in, and what comes out may have only electric field in one direction. And that ray, that was absorbed. So what comes out has electric field just going up and down. So I could take one of these, and I could put another one behind it, it makes no difference. Why is that? So this one absorbs light, I'm dimmer. That one absorbs light, I'm dimmer. I put two of them here. The second one doesn't make it any dimmer. Why is that? Yeah.
It's like both polarizing in the same direction.
Pardon me?
Both are polarizing them in the
They're
same
both
direction.
polarized the same way. So here's the polarizer. It absorbed the horizontal light. The vertical light came through. So if I put another one here, and this also absorbs in that direction, it makes no difference. The vertical light will still, the vertical polarization of electric field still goes through. So what do you think is going to happen if I take this and I rotate it 90 degrees? This polarized by the same argument.
It's going to be dimmer.
If I rotate it at 90 degrees, now it's going to absorb this, right? Can't see me anymore. So I'll pass these around, you can play with them. One other thing that's interesting, just put one in front of your laptop screen and rotate it, just one. What does that tell you about the light coming out of your laptop screen? Do it against so you can see it. Now it's very bright. Now, you go from one point there, you see a nothing coming out of the laptop screen. What does it tell you about the light coming out of the laptop screen?
It's polarized.
It must be polarized. It must be polarized. And at least on this one. And if we have time in the course, I'll talk about display technology, and we'll see what polarization is. So anyway, that's I don't want to use the word proof, but it's some practical concept that gives you a feel for the idea of electric fields in rays of light, electromagnetic wave. All right. So anyway, polarizer and the light that came out. We say the light that came out was polarized because it had its electric field pointing in one direction versus the other. So some practical consequences. Now, let me pull up the slide I pulled up last time. I just want to emphasize, this idea of a spectrum, and then we're going to talk about important consequences of that, which are multi-billion-dollar consequences. So I am going to put up the one of the figures from last time. I have 3 or 4 copies, maybe half a dozen copies left. Anybody not get this figure last time? Okay, anybody else want a copy? Okay. And while we're at it, we have another one today. Oops. One for you. And here's one for you guys. Here's one for you guys. So I just wanted to emphasize that we call light at different frequencies, we call it different things. And we're my pointer doesn't work here. There must be a way to make that work. I don't know how. Let's try that. Whoops. Okay, forget that. So what I plot here is frequency in hertz. It's called Hertz because Hertz was the first person to experimentally create an electromagnetic wave and detect it. It was part of the proof that they really existed. That was in the late 1880s. And let's start with light that you can see. Visible light has a frequency here, somewhere between 10 to the 14 and 10 to the 15 hertz. The wavelength, well, we worked it out in class, is something like a fraction of a micron. So that's just that little piece of the spectrum. The frequencies here I vary by a factor of 100, that's so-called logarithmic scale. We start over on the left with frequencies of 10,000 cycles per second, and on the right we're up to 10 to the 20, whatever you call 10 to the 20 cycles per second. When we talked about light, I think we did this at the beginning of the course, if the wavelength is a bit more off the red side of what you can see, you know what we call that light? If it's too far to the red so you can't see it?
Infrared?
Infrared. Did I use the word infrared? No, yeah, I did. So here's red. That would be lower frequency is longer wavelength. We call that infrared light. And if you go near something hot, and you can't, let's say it's not even red hot, it's just hot, like maybe an oven, and it feels hot, what you're feeling is an infrared light coming from that thing towards you. And that's what that heat feeling is. On the other hand, if we go to the right, higher frequencies mean shorter wavelength in blue. We call that ultraviolet. I guess you could call it infraviolet, but they call it ultraviolet. So there's UV light on the right. And if you get about a factor of 100 in wavelength shorter than visible light, so the wavelength might be about a micron divided by 100, which means 10 nanometers. That's what we start to call X-rays. So when you go to the doctor's office and get X-rays, they're somewhere in that general range of 10 to the 18 hertz, maybe factor of 10 either way. The wavelengths down in the nanometer range. And if you go to lower wavelengths, those are known as various types of radio waves or microwaves. For example, a microwave oven, you see at the very top, operates at 2 gigahertz, 2 times 10 to the 9 hertz. Microwave ovens. And there are other things I listed, broadcast TV, AM radio, FM radio, shortwave radio, satellite TV, Wi-Fi, cell phones, they're all over the place. And it's all very tightly regulated because, for example, when you turn on your microwave oven, you don't want to be sending out radio waves at the same signal that your Wi-Fi is working on because they're going to interfere with each other. And you don't want your Wi-Fi interfering with your cell phone, with your TV, and all those things. So anyway, all that's very tightly regulated by the government. And we're going to talk a lot about that later. If you're a cell phone company and you want to set up shop, you need some frequency at which you're going to send your cell phone signals. But it has to be different than someone else's cell phone frequency, right? So then the question is, that we're going to get to in a minute, is if I just have one exact frequency, how much information can I send? And if I need more than one exact frequency, how much do I need? And how much information can I send on my cell phone network? That's going to be the focus of today's lecture. Questions about that diagram? So let's let me turn off the projector here for a minute. So for the next half hour, I'm going to introduce a concept goes bandwidth. And this means what range, some range of frequencies. A range of frequencies, or a band of frequencies. And let's take, for example, suppose I'm designing a radio or a cell phone. And suppose I'm trying to transmit is a voice signal. And so I have my goal as to transmit some audio, let's say audio, which just means voice. And that, as we described, we could represent signals by voltages. Maybe we had a microphone somewhere, and we created a voltage V audio of time, which represents what we're trying to send. That's you speaking into a cell phone, that's what we want to transmit. And it's a voltage on a wire. And